Hi there. So this preview is designed to give you an introduction to rational functions and their graphs. So with that said, we'll dive right in. The equation of a rational function is a ratio of two polynomial expressions. So I've just given you two examples down here below of rational functions. So the first example, y equals 1 over x, and then you can see the example over on the right. But there are numerous examples of what an example of a rational function. Just below that in example 1, they want us to look at these graphs below. These are all examples of what rational functions would look like graphically. And together I want us to label the horizontal and vertical asymptotes. So horizontal and vertical asymptotes are lines that your graphs approach and rarely touch. And we'll talk a little bit more about that in here in a few moments. So in letter A here, I would say that this vertical line here, that would be referred to as a vertical asymptote. Asymptotes are always equations of lines, and so since this is a vertical line, that its equation would be x equals -2. Then you can see this horizontal dashed line here. That would be a horizontal asymptote. I'm just abbreviating here with VA and HA for here horizontal asymptote. Horizontal asymptotes are always y equals, and it's crossing the y-axis at +2. Okay. So if we scoot over to letter B, hopefully you recognize, okay, I've got two sets of dashed lines here, so I'm going to have two vertical asymptotes this time. So I've got a vertical asymptote on the left and the right. Those will be x equals -1 and x equals, hopefully you agree, +1. The other asymptote here is a little harder to see, but it's actually the x-axis here, which happens to have an equation, horizontal asymptote, of the line y equals 0. Okay, so we'll talk a little bit more about that as we move on through this preview. And then here in the last, in letter C, hopefully you agree, okay, I've got a straight up and down dashed line, so that's a vertical asymptote, x equals, and that looks like it's at -3. And then I have a horizontal asymptote at y equals +1. That's a y. There we go. All right, so you'll sort of see here how the graphs are hugging those asymptotes, okay? Vertical asymptotes are used to show domain restrictions because if you think about it, as we've been working through this course, when we've talked about domain in the past, we've seen graphs like this and we've said, oh, okay, well here's a portion of your graph from -infinity to -2, and then we picked back up for this portion of the graph and said, okay, it goes now from -2 to +infinity. So that's another way to think about vertical asymptotes. The graph of a function will never cross a vertical asymptote. Okay, so we'll move on down here to example 2. In example 2, they want to know what are the domain restrictions for each rational function. And if you recall, this really isn't going to be that much different from what I've had you do in the past when I've asked you to find the domain for me. When I've asked you to find the domain, if you have a denominator, we've said, oh, well, this denominator cannot equal 0. So what we end up doing is we need a factor down here. So the only way to multiply to give you x squared, x and x. You've got two ways to multiply to give you 4. If we use 2 and 2, there's no way we're going to get a 3 out of that. But we can use 4 and 1. We want a -3 in the center, so we do our outside. For me, I'm getting 1x. Inside, 4x. My goal is that middle term, which is a -3x. The only way I'm going to get a -3x would be to make 4 negative. So -4, +1. And then if you recall from here, when we've gone to find our domain restrictions, then we set x -4. We said that can't equal 0, and x plus 1 cannot equal 0. And then we go through the steps of solving. So we know we add 4 to both sides. So now we know x cannot equal +4. And we come over here, subtract 1 from both sides, and we say x cannot equal -1. So those would be your domain restrictions here, okay? You'll in a moment see a correlation between those domain restrictions and your vertical asymptotes, okay? I'm going to let you pause the video and try letter B and take that one from top to bottom to find the domain restrictions. And then we'll move on down here below. It says a horizontal asymptote of a graph of a rational function is used to indicate the end behavior. Okay, something we've already talked about in this section. It's going to be looking at the end behavior of the function. It is possible that a graph will intersect a horizontal asymptote. It's pretty rare, but it can happen, and so just so you're aware of that. You cannot, as I mentioned up here, you cannot cross a vertical asymptote, but it is possible to cross a horizontal. Just below that, the graph of a rational function will get very close to your horizontal asymptote when the x values of the function are very small or very large. And what I mean by that is if I come back up here and look at these graphs, as you see how the graph approaches that horizontal asymptote as it gets really, really small. And on here on the right-hand side, as my x values get larger and larger, it's approaching that horizontal asymptote. It doesn't matter which horizontal asymptote I'm looking at, but that's the idea there, okay? Just down here below, the last piece on this page, it says look at graph C above in example 1, so back where I just was. What does this graph have that the graphs A and B do not have? And hopefully you might have already kind of noticed it before when we were up here identifying horizontal and vertical asymptotes. It has a hole, and I'm going to highlight it for you. See this point right here? That is referred to as a hole in the graph, and so there is another element that we'll be focusing on here in just a moment. But for now, we're just going to note that that graph has a hole in it. So the graph has a hole that the others do not have. All right, I'm going to flip it on over. At the top of the next page, we talk about domain restrictions. So sometimes a domain restriction corresponds to the vertical asymptotes of your function. Other times that domain restriction corresponds to a hole in the graph of the function, okay? So the question below here was, well, how are we going to know if a domain restriction will correspond to a vertical asymptote or correspond to a hole in the graph? And at this point, you don't know that, but that's for, I'm here to tell you that you will always factor the numerator and denominator. So let's write this out. You're going to factor numerator and denominator. I'm just going to abbreviate here. So you factor your numerator and denominator. If a factor cancels out, then there is a hole at that location. If nothing cancels out, all terms in the denominator, all terms in the denominator are set equal to 0 and solved. Those will be vertical asymptotes. Just going to abbreviate, okay? So essentially, you're going to factor. We've been doing that, okay? So you're going to factor your numerator and denominator. If you have a factor that cancels out, that's going to create a hole. And if you don't have anything that cancels out, then everything in your denominator will correspond then to vertical asymptotes. All right, so just below that, and we'll hammer this out with some specific examples here in just a moment. In behavior, how do you find the in behavior of a rational function? All of the rational functions that we're going to study here in Math 171 will have in behavior described by either a horizontal asymptote or a slant/oblique asymptote. Slant and oblique asymptotes are the same thing. It just depends on how you might have been exposed to it in a prior math class. So I used both terminologies there. Just below that, I say, well, how many horizontal asymptotes can the graph of rational function have? It can only have one. So just so you're aware of that. You have multiple, as you've seen on the previous page. You can have multiple vertical asymptotes, but you can only have one horizontal asymptote. And you might be asking why. And that's because each rational function can only have one in behavior. Okay, so each rational function can only have one type of in behavior. And so if you had more, so that, like we said, horizontal, your in in behavior will be defined by your horizontal and oblique asymptotes. When you sketch a rational function in here in this class, you're always going to indicate that your function gets very, very close to your horizontal asymptote on the far left and far right side of your graph, okay? Hugging the asymptotes, that's what I like to say. All right, so how do we find horizontal asymptotes? Horizontal asymptotes are based on the degree. So you will compare the degree of the polynomial in the numerator to the degree of the polynomial in the denominator, okay? If they are the same degree, then you're going to find the ratio of the leading coefficients. The horizontal asymptote will have the equation y equals that ratio. So, for example, if I gave you y equals 2x squared minus 9 over 4x squared minus 7x, and I said, okay, well, let's find the horizontal asymptote here, we would notice that the degree of the top is 2, the degree of the bottom is 2, so therefore they have the same degree. So then my horizontal asymptote would be the line y equals, and I would take these coefficients here in front, 2 over 4. If you can ever reduce, you will, and here we can. 2/4 will reduce to 1/2, and that would be your horizontal asymptote. Okay. Your next scenario says that if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, so meaning the degree of the top is less than the degree of the bottom, then your horizontal asymptote will have the equation y equals 0. So the example I'll give you here, we'll say we have y equals 2x minus 9 up top over x squared plus 1, so hopefully you agree. The degree of the top is 1, the degree of the bottom is 2, so the degree of the top is less than the degree of the bottom. So there's no work to show. Your horizontal asymptote is the line y equals 0. Final answer. Okay. And then there would be one more scenario. If the degree of the polynomial in the numerator is more than, I should have highlighted that here for you, underlined, I'll try to remember to go back and do that, is more than the degree of the polynomial in the denominator, then the rational function will not have a horizontal asymptote. Instead, if the degree of the numerator is just 1 more than the degree of the denominator, then we'll have what's referred to as a slant or oblique asymptote. Remember, slant and oblique are synonyms with one another, so however you've been exposed to it in the past. We can use long division or synthetic division to find that oblique asymptote. So that's what I'll do down here below for you. Let's give you a couple of examples. So let's say we had y equals x squared minus 9 over x plus 1. So we can see here the degree of the top is larger than the degree of the bottom. So for that reason, we have no horizontal asymptote. But you do notice if you look at your degree, the degree at the top is 2, the degree on the bottom is 1. So it's only, I like to call these top heavy, it's only top heavy by 1. So since it's only top heavy by 1, it will have an oblique asymptote. So it will have an oblique, I'm just going to abbreviate as well, oblique asymptote. Like I said, you find that oblique asymptote either using long division or synthetic division. Let's go ahead and find that here. So to find my oblique asymptote, you're going to be dividing by x plus 1. So out here in synthetic division, I can put the opposite of that plus 1, so put in -1. Line up my coefficients up top, remember in descending order, so x squared, you don't have an x term, so you need a placeholder of 0, and then you have your number. Skip a space, remember above the line you add or subtract, below the line you multiply, bring down that 1, -1 times 1, -1, add, gives me -1, -1 times -1, +1, add those together, you have -8. Remember, this is 1 power less, so this is x and number. So my oblique asymptote would be the line y equals x minus 1. And that would be your final answer there. It does not have a horizontal asymptote, so no horizontal asymptote, but it does have an oblique asymptote. Oblique asymptotes are always linear lines, a slope and a y-intercept, okay? Let me give you another example down here. So let's say we have y equals x cubed minus 2x plus 1 over x plus 3. So I can see here that the degree of the top is definitely bigger than the degree of the bottom, so it's top heavy. So with that said, then I automatically know I have no horizontal asymptote because it's top heavy. Oblique asymptote only occurs if you're top heavy by 1. The degree up here is 3. The degree down here is 1. If you subtract those, you're top heavy by 2. So you also have no oblique asymptote here either. Okay, so just so you're aware of that. Okay. Now, I'm going to flip it on over. Top of the next page in example 3 is asking you to find your just asking solely for horizontal asymptotes here. What I would recommend that you do is to pause this video and try these for yourself, comparing back to your, remember you're just looking at the degree. Ask yourself, is the degree the same? Is it smaller up top, or is it top heavy? In any of those cases, then find out what your horizontal asymptotes are. So, and then come back to the video. I want to go ahead and give you some explanation though. Here in example 1, you can notice that the degree of the top is the exact same as the degree of the bottom. So I do have a horizontal asymptote then at y equals, and I just pull my coefficients, 1 over 2. Final answer. All right, moving on down to the next one. I can see that the degree of the top is 1. The degree of the bottom is 2. When the degree of the top is less than the degree of the bottom, that means we have a horizontal asymptote at the line y equals 0. Something that might help you with this, if you notice on the bottom you have x squared, you could write this as 0x squared, and then you could think of this over here as like, oh, well, this is 0 over 1, which is just 0. Okay, that's really where it comes from, but you know, if that helps you any. But essentially all I need to say here then is that it's the line y equals 0. Final answer. Then down here in bottom in number 3, the degree of the top is bigger than the degree of the bottom, so that means we have no horizontal asymptote. But you can see that you are only here top heavy by 1, so you would have an oblique asymptote. So yes, you would have an oblique asymptote. I think it's worth again showing you the process to find that oblique asymptote. So let's use synthetic division again because we can, since we don't have a number in front of our x. We take the opposite of this positive 1 down here, so negative 1. Line up my coefficients, and so that gives me 1, 6, and negative 7. Above the line we add or subtract, below the line we multiply. Bring down that 1. Negative 1 times 1 will give me negative 1. 6 minus 1 will give me 5. Negative 1 times 5 give me negative 5. I get a remainder. It doesn't really matter what that remainder is. I'm only concerned about this, which is 1 power less, so x and then number. So I have an oblique asymptote, and it's the line y equals x plus 5. All right. In the last two examples, we're going to explore how do we graph a rational function from top to bottom, okay? And we're trying to be as precise as we can. So looking here at example 3, they want to, at the very beginning, in part A, they say, well, what are the domain restrictions? So if you remember, to find these domain restrictions, we need to factor. So up here at the top, can't do anything, so I have 5x minus 3. But on the bottom, and we factored this back on the front page, so I'm just going to go ahead and repeat that. It was minus 4 plus 1. So our domain restrictions, as we did back previously on the front page, well, we said, okay, well, x minus 4 can't equal 0, and x plus 1 cannot equal 0, and we solved for x in both cases, so x could not equal positive 4, x could not equal negative 1. Part B wants us to give the coordinates of any holes in this graph. If there aren't any holes, then we'll just write none. Remember, holes only occur whenever factors cancel out. I do not have any factors here that are going to cancel out, so we have no holes in this graph. Part C wants vertical asymptotes. Your vertical asymptotes then are just your denominators set equal to 0. So x minus 4 equal to 0, x plus 1 equal to 0. And if we solve for x, we know we're going to get a positive 4 and a negative 1. Part D says give the equation of your horizontal asymptote. So you can look back at your original function. It's probably the easiest way to look at it, because here you can see up top you have degree 1, and on the bottom you have degree 2. So the degree of the top is less than the degree of the bottom, so that would be the line y equals 0. Part E wants us to find the x-intercepts. If you remember, x-intercepts, that's where we let y equal 0 and we solve for x. So I'm going to take my function that you had in the very beginning, 5x minus 3 over the x squared minus 3x minus 4, set it equal to 0, right? Because that's your I'll come back up here. Your f of x, that's y, so I'm setting this equal to 0. It's legal to put a 1 underneath that and then just cross multiply. The nice thing about that is, though, 1 times the 5x minus 3 just gives me 5x minus 3, and that whole piece down there times 0, that's just 0, so that's nice. We add 3 to both sides. 5x equals 3, divide by 5, so x equals 3/5. So I would be crossing the x-axis at 3/5. Now to find your y-intercept, if you recall, we've done this quite a bit. This is where you let x equal 0 and you solve for y. So if you let x equal 0 and you solve for y, I'm just going to go back to this problem, your equation here. So then you have, everywhere you see an x, you're plugging in 0. On the bottom, 0 squared minus 3 times 0 minus 4. So up top, that just leaves you with negative 3. On the bottom, that just leaves you with negative 4. A negative over a negative gives you a positive 3/4. Now, let's come over here to the graph and let's put in what we know. We had vertical asymptotes at positive 4 and negative 1. Those are our vertical asymptotes. And we also had a horizontal asymptote at the line y equals 0, which happens to be your x-axis. Okay. Then let's plot those x and y intercepts. So from here we know that we are crossing the x-axis at 3/5. So 3/5 is 0.6, so just a little bit past a half there. And 3/4 is 0.75, so almost to that 1. Make my graph a little smaller here, pen a little smaller. Now, unfortunately, we don't know what's happening over here on to the left of that negative 1 and to the right of that positive 4. So we'll tackle that in just a second. But here in the middle part, since you have x and y intercepts and you know that you have to hug these asymptotes, then you can generate the graph through here. Rough sketch, but you are hugging those asymptotes and you have to pass through your x and y intercept. Now to figure out what's happening over here on the right hand side and over here on the left hand side, we just do a little bit of a test point. So we're going to let x equal negative 5, for example, and we go to our original function. So 5 times negative 5 minus 3 over negative 5 squared minus 3 times negative 5 minus 4. We just sort of clean this up. So negative 5 times negative 5, that's going to give me negative 25 minus 3. On the bottom, take a negative 5 squared. That gives us positive 25. Next term, negative times negative, give me positive 15 minus 4. Clean up, I ended up with negative 28, excuse me. On the bottom, 25 plus 15, 40 minus 4 will be 36. Then you can just throw that in your calculator. I know it'll reduce, but we need a decimal, so we'll be able to plot it. You should get a negative 0.78. So it says, okay, when we put in an x value of negative 5, we got out a y value of 0.75. So that's our point there. Now, knowing that you're above that horizontal asymptote, use the horizontal asymptotes now to guide you through that portion. You can't have anything down here below it, but you know that you'll need to hug your horizontal and vertical asymptotes. We repeat that same process with x equals positive 5. So I go to my function. Everywhere I see an x, this time I'm plugging in positive 5. So that'll be 5 times 5 minus 3 up top. Positive 5 squared minus 3 times positive 5 minus 4. Up top we subtract, so that'll be 25 minus 3. On the bottom, 25 minus 15 minus 4. That'll land us at 22 over 6. Again, just throw that in your calculator, get it approximated. Should be about 3.67. So what this tells us, if we put in an x value of positive 5, we get a y value of 3.67. And that just tells me again that my graph has to pass through that function and hug these asymptotes. So that graph that you see there, that is the part in blue, that is the graph of the rational function, and those red lines are your asymptotes helping to guide you through that. This is an example of a graph that does cross the horizontal asymptote, though. You can see that because of the x-intercept. Okay. All right, let's flip it on over. You know, it might be a good idea for you to try and do as much of example 4 as you possibly can solo, and then come back to the video to get an explanation for anything that you missed, okay? Or you get stuck on, okay? So here in example 4, first thing I would do at the very top, take this function and let's factor it. So up top I can factor out an x. On the bottom, the only way to multiply to give me x squared, x times x. Most common way to multiply to give me 15. 5 times 3. I need a positive 8 in the center, so I need to make them both positive. And positive 5 times positive 3 gives me that positive 15. You'll notice here this time that those x plus 5s cancel out. So we have a term now that's canceling out. So hopefully you remember, okay, that's going to cue us something new is going to happen here in this graph. And then you'll have x over x plus 3. In your 171 class, I'm going to refer to this function here as the reduced function. Okay, and that reduced function can be easier to work with than the original function. The domain restrictions will come from the original function. So remember, that's where x plus 5 cannot equal 0 and x plus 3 cannot equal 0. So we solve these and we find, okay, well, x can't equal negative 5. Here, x cannot equal negative 3. So those are our domain restrictions. In part B, and I wrote it like that, but remember, as far as, if we wanted to write, those are the domain restrictions, but if we wanted to write the full domain, just so you recognize, okay, well, this really means negative infinity to negative 5, then negative 5 to negative 3, and then negative 3 to positive infinity, just so you have that correlation between, what we've been doing in the past. Okay, it means the same thing. Part B wants us to give the coordinate of any holes in the graph. So like we said, we had this x plus 5 cancel out. So since x plus 5 was a factor that canceled out, you set that equal to 0, solve for x. So x equals negative 5. We're going to have a hole at negative 5. To find the y value of your hole, you take this x value here and plug it into the reduced function. So you're going to take that negative 5 and plug it into the reduced function here. So that would be negative 5 plus 3. And so that'll land you at negative 5 over negative 2. A negative over a negative gives you a positive. Try that again. Positive 5/2, which you know to be 2.5. Okay, so you're going to have a hole at negative 5, 2.5. Okay. Part C wants your vertical asymptotes. So looking at your reduced function, let me highlight that reduced function up here. This reduced function up here. Looking at your reduced function now, vertical asymptotes are anything that's left in that denominator. So you have x plus 3 left in that denominator. Set that equal to 0. Subtract 3 from both sides. So x equals negative 3. That's a vertical asymptote. Your one and only vertical asymptote here. Okay. Letter D wants your horizontal asymptote. You can, with the horizontal asymptote, you can go back to the original function, or you can still use your reduced function. Either way, I'll show you. If you look at the original function, the degree of the top is the same as the degree of the bottom. So you just take your coefficients. It would be y equals 1 over 1. Notice over here with the reduced function, the degrees are the same on the top and bottom. The coefficients are still 1 over 1. So that's going to reduce and give us a horizontal asymptote at y equals 1. Okay. In letter E, it wants us to find the x-intercept. You can again use your reduced function. All right, that's an easier function to work with here. So x over x plus 3. And in your 171 class, I provide you with a full kind of like cheat sheet for the steps for doing this. Okay, so just, I mean, I know, recognize this is the first time you're doing it here in this preview, but as you move forward, just so you know, in your 171 class, you have a full little sheet there that'll tell you when you can use your reduced function, when to use the full function, and what are you setting equal to 0, and so forth. Okay, so for your x-intercept here, remember you're setting your function equal to 0. You put a 1 underneath that 0 and cross multiply. So here if we cross multiply, 1 times x is just x. X plus 3 times 0 is 0. So you have an x-intercept then at 0, 0. That's an x-intercept. To find your y-intercept, again, you can just use your reduced function, plug 0 in for x, and solve for y. So for that reduced function, I have 0 over 0 plus 3. 0 divided by anything is still 0. You know, just so you hopefully are putting this together. Anytime 0, 0 is an x-intercept, that will automatically be your y-intercept. All right, let's come down here and kind of crank out our graph. We can see that we had x-intercept. We had a, excuse me. Let's start with our asymptotes first. We had a a vertical asymptote at -3. Sooner or later, I'll get it out. Okay, so we got a vertical asymptote at -3. We had a horizontal asymptote at +1. And we had a hole at -5, 5/2. So let me make my pen a little smaller. I had a hole at -5, 5/2. So remember, 5/2 is 2.5. So I'm just going to make that little hole there. And I had an x and a y-intercept down here at 0, 0. This time, we've got everything that we need. We can tell up here in this top quadrant that I have to come really close to this hole. I just won't equal it. And hug my asymptotes. And then down here on the bottom right, I'm going to hug these asymptotes and then be sure that I pass through that x and y intercept there. And that's your final graph there. You wouldn't have anything in those other two quadrants, okay? Always opposing one another. All right, let me know if you need anything. Thanks a lot. Bye.